Okay, I wanted to show you where you could find the information about the hovercraft lab. And of course, if you go to classes and then scroll down, physics. Here's the hovercraft data over here, and basically it's the printout from the motion detector, and it gives you a lot of information. It gives you a distance time graph, a velocity time graph. I already drew in the best fit line, and the equation is given. From that equation, the slope is equal to the acceleration, so you could get the acceleration off of that. Now, you know how we also collect the data with stopwatches and meter sticks? Okay, we're not even going to use that data. Originally, I told you you're going to have to make your own distance versus time squared graph, and the slope of that would equal 1/2 the acceleration from the great distance formula. You're not going to have to do that. So basically, you're just going to use the graph, print this out over here, and staple it in your lab notebook, and you're going to use the acceleration. And then just some reminders here. A little slow to load here. The main question of the lab is, what is the acceleration due to gravity? In the background information, I want you to explain how the motion detector works. In your calculation, folks, basically these 5 things. Use the slope from the velocity time graph obtained from the motion detector to get the acceleration down the ramp. Draw a free body diagram. Draw a second free body diagram including the components of the weight force. Show the derivation of G equals A parallel over sine theta. We did that in class. And then calculate G and the acceleration percent error. Okay? And then be sure to include all sections of the discussion. So that'll be due a week from today. Okay? We're going to be working on 3 questions. The first is, what is an electrical current? Okay. So we're moving from static electricity to current electricity. Static electricity is when you have charge that's just hanging out somewhere. It's like still, basically. Current electricity is when the charge is flowing from one place to another. You can think of static electricity as being like a stagnant pond where the water is still, and current electricity being like a flowing river where the water is flowing, from one place to another. What is electrical current? What is an EMF? And what 2 things are required to have a simple circuit? Everyone ready, Freddie? let's say we start off with two objects, and let's say this object over here has 4 extra electrons on it, and let's say this object over here is missing 4 electrons. So the charge of this object over here, -4 elementary units, and the charge of this object over here, +4 elementary units. And we did problems with these metal spheres. If you touch these two spheres together, or if you connected a wire between these spheres, would the charges remain -4 and +4? Does anyone remember how to play that game? What would be the final charge on each of the objects? Paul?
It would be the average sum of
Yeah,
both.
it'd be the average of 2. And in this case, what would that average be?
0.
Yeah, they would both be neutral, 0 and 0. So we're going to take a closer look at that. And let's suppose this time we connect a wire, but this wire now is going to go through a light bulb, and then it's going to go to the other charge. So basically up here we have a light bulb. Now we know light charges repel, so these extra electrons are going to be like, hey, get away from me, get away, yeah, you know. So some of the electrons are going to start flowing through the wire this way, and when they flow through the wire, they're going to go through the filament of the light bulb, and as they go through that filament of the light bulb, they bang into atoms that are in the way, and when they bang into atoms that are in the way, those atoms have electrons that get bumped into excited states. And then when those electrons drop back down to their normal levels, light is given off. Yes? So basically, as long as we have electrons flowing through the wire like this, we're going to have light being given off up there like that. And basically, this flow of charge, yes, is called an electric current. And if you have a lot of charge flowing through that wire, then you have a big current. If you have just a little bit of charge flowing through the wire, you know, then it's a small current. So let's define electric current. Current is the rate of the charge flow. Now, we've seen that word rate before. You guys should automatically be able to write the defining formula for current. I'll start you off. Current equals something divided by something else. It's the rate of charge flow. And if you understand how rates work, you should be able to fill in those two blanks. What do you say, Dylan? What do you think it's going to be? What over what?
Charge over time.
That's what I'm talking about. It's the amount of charge going through the wire divided by how much time it took to go through the wire. If you wanted to write the formula out in symbols, the symbol for time, T, the symbol for charge is a Q, but the symbol for current is kind of a weird one. It's I. Alright?
I
I equals Q over T. For example, let's say you have a wire, and let's say that there is 5 coulombs flowing through that wire, okay, every 2 seconds. And the question is, what is the electric current? So we come right to here. We know it's charge per time. So 5 coulombs pass a fixed point every 2 seconds. So in our little example here, 5 divided by 2 is going to be 2.5. And then what you see is what you get with the units at first. So it's 2.5 coulombs per second. And those are great units for current because they're self-explanatory. That means you have 2.5 coulombs of charge going through that wire each second. Keep in mind though, that doesn't mean there's 2.5 electrons going through there, each second. A coulomb is a big gang of electrons. So, recall, 1 coulomb is equal to a big gang of electrons. So, I always think of that because a coulomb is a humongous gang of electrons. So, if you have a current, okay, of 2.5 coulombs per second in a wire, okay, well, it's going to be 2.5 times that many elementary charges going through each second, yes? Now, to honor a scientist who did a lot of work with electricity, a coulomb per second also has another name. Reed, do you know what it is? An ampere. Andre Ampere. Unfortunately, though, it's so easy to forget the meaning. Like coulombs per second, those are great units because it's, self-explanatory. Oh, there's 2.5 coulombs going through the wire each second. But 2 amperes, it's very easy to forget the meaning. So every time you read that word ampere, you should automatically train your brain to think of coulombs per second. So if I say ampere, you guys say coulombs per second. Ampere.
Coulombs per second.
Ampere.
Coulombs per
Ampere.
second. Coulombs per second.
That's what I'm talking about. So the electric current measured in coulombs per second is a measure of how much charge is flowing through the wire as it goes through the light bulb from the negative terminal to the positive terminal. Now, would this current flow forever? No, it would be very short-lived. Okay? Basically, as soon as those 4 electrons go over, as soon as those 4 extra electrons go over, both charges would be neutral, current would stop. So if I want to keep that current going, what I have to do is, every single time an electron flows across and ends up going over here, yes? Every time an electron flows across over to here, I have to have some sort of mechanism to put it back on the negative terminal. If I could keep, take my hand here, here's my thumb, my fingers are here. If I could take my hand and pick up this electron right here, yes, and I could physically put it back over here, and let's say I could do it as fast as they come over. Maybe I would be using 2 hands like this. The electrons are naturally coming over because like charges repel, yes? So over here, the electrons are naturally coming over, yes? But I'm going to be using two hands, and I'm going to be putting them back this way as fast as they come over, like this, you know. If I keep putting them back to the left as fast as they come over to the right, then guess what the light bulb would do? It would stay on. It would stay lit. Yes? That's called a steady current. Okay? That's a little different than going steady with like a boy or a girl. You know, that's something different. This is a steady current where it keeps flowing in the same direction at the same rate. Now, this green arrow, this mechanism to put the electrons back on the negative terminal, it has a name. It's called the EMF. That's an acronym. I don't want to tell you quite yet what the acronym stands for because it's misleading. Okay? So, an EMF. An EMF is a device that puts the electrons back on the negative terminal just as fast as they naturally flow through the wire above. And it's not going to be easy. You know, if I was doing it by hand, I would get tired after a while. Because as I pluck the electron away from the positive, it's going to be like, no, don't take me from the positive. I love positive. And then as I bring it over towards the negative, it's going to be like, oh, I hate negative. It's going to be repelling. So what am I going to have to be doing the whole time as I drag that sucker over? Work. It's going to take a lot of work. In order to do the work, you know, it takes an energy source. You know, so an EMF sometimes is thought of as a source of energy. Now, essentially, there's two EMFs that we're going to be dealing with. One, Mr. Ruth. A battery. A battery uses chemical energy, stored up chemical energy via chemical reactions to put that electron back over. I have a little demonstration I could show you. Another type of EMF is a generator. A generator uses a magnetic force to put the electrons back so that they'll naturally flow over. We're going to learn more about magnetic generators in the next unit on magnetism. I happen to have one here to demonstrate. Now, basically, you have the horseshoe magnets, and my diagram's kind of messed up, but you got the horseshoe magnets, and you have a loop of wire inside the horseshoe magnets, which is connected to a crank, and basically, these are connected to two wires, and then you could connect this one to your light bulb and this one to your other one. And this whole device right here is called a generator. And by cranking the handle, you could generate electricity. So that's another example of an EMF. And again, keep in mind, folks, when I say EMF, you should be thinking of this diagram here, where the electrons are being put back on the negative terminal just as fast as they're coming across that top wire. Now, all of the electricity that we get from wall outlets is produced by magnetic generators. So if you go to like LIPA and you go into their facility, they hire like hundreds of people to crank the magnets to produce the electricity that you guys use at your homes.
Sure.
No, of course they don't do that. Yes? So the question is, how do they crank the handle? Well, instead of using a crank like that, okay, you could take a big fan and there's a lot of different ways you could turn that fan. You could use natural wind to turn the fan, and basically what do you have? A windmill. Okay? You're not even burning anything. No carbon dioxide produced. Okay? Another thing you could do is you could put that fan thing under a waterfall and let the waterfall spin the fan. That cranks the handle. Yes? Most of the electricity produced on Long Island, okay, has another mechanism of turning the fan. Imagine a big tea kettle filled with water. You heat the tea kettle, the water turns to steam, the steam blows out, turns the fan, cranks the handle, generates the electricity, and the light goes off. Now the only thing is, you have to heat the water. And most of the electricity that is produced on Long Island uses natural gas, basically like a big Bunsen burner, all right? To heat the water, to turn it to steam, to blow it up against the fan. There's a special name for the fan called a turbine. Turbine is just a fancy word for the fan that gets spun. Now there's another way to heat the water, and that is you could use nuclear energy. Okay. With nuclear energy, you have these fuel rods, and these fuel rods contain uranium atoms, which are big, unstable atoms. And basically, if you shoot neutron particles at the uranium, the neutron comes in, hits the uranium, busts it up, and it actually forms two smaller atoms. And when that big atom breaks into smaller atoms, that's called fission, and lots of energy is released. And you could stick these fuel rods in water, and it's like shh, creates steam, which could be used to turn the turbine and generate the electricity. The good thing with nuclear energy, it doesn't produce any carbon dioxide. You're not burning anything. The bad news is, after that uranium atom splits, fission, and you have those smaller atoms, yes, all right, they're highly radioactive, right? They give off lots of dangerous, particles and invisible light that is known to give people health problems. And the problem in Japan right now is not in the nuclear reactor itself, but you see these fuel rods here. After you're done using them, and you got the leftover stuff, no one knows what to do with the leftover stuff. So basically, they just store it on site. And at those nuclear power plants in Japan, they had these storage facilities where those used fuel rods were just kind of hanging out, and they used to keep them soaking in water, right? For two reasons. The water would shield any of the dangerous radioactive stuff, coming off of them. And two, the water was used to keep them cool. And then after the earthquake, the tank cracked and the electricity went out, so there was no way to pump water in to those used fuel rods. So basically, they're overheating. And they give off so much dangerous stuff, you can't even go near the place. And of course, it's invisible, you can't see it. So it's like scary stuff. Okay. Take a break, come on back.